Yeah. Yeah, I usually
Felt
turn
like you were
these
lecturing.
on.
It would be lecturing.
Yeah, to a sleepy audience. Okay, I'll get started. Welcome to lecture 5 of our IAP course on causality. We're continuing to talk about causal structure learning. Y'all are going to notice there are now cameras, and there's no longer my voice coming through the ceiling. So if I'm not loud enough, please let me know to speak up. I just had some issues with the recordings in person, so I re-recorded those. Those are on YouTube now, so you should be able to watch those recordings. And then I'm just going to be posting that myself from now on. We have PSET 2 due on Thursday. A bunch of y'all turned in PSET 1. That will be returned after class. People did pretty well. PSET 2 is going to be about the algorithm that we're talking about today, the PC algorithm. That's the bulk of it. And if you want to work with people on that or ask us some questions or something, then there's going to be a study session tomorrow in the same room as the study session was last week. So that's 24307. So I want to start off by recalling some of the things that we proved in the last lecture that are going to be important for what we're doing today. So from the last lecture, we showed that two DAGs G and G prime are Markov equivalent. And this definition was that they had the same D separations. So that was that these two sets are the same. If and only if they have the same first skeletons and second unshielded colliders. So it's going to be useful to talk about kind of a representation of this Markov equivalence class in terms of just a single graph. And that's going to give us the first definition of our lecture today. So since they have the same skeleton, we can use this graph, just the same exact skeleton for it. And then what we're going to do is we're going to have some undirected edges and some directed edges. So this is going to be called the essential graph. Of a Markov equivalence class. Has the same skeleton as any G DAG in that Markov equivalence class, and the edges are going to be, we're going to have a directed edge xi, xj, only if that edge is in that direction for all of the graphs in the Markov equivalence class. And if we take some G in that Markov equivalence class, we're just going to represent the essential graph of it by this holographic E of G. So for example, if we have our graph, I'll just do the top 4 vertices here. So I'll exclude x5. We said that they're going to have the same unshielded colliders, so all the graphs in the Markov equivalence class will have this edge. But then we can reverse either of these edges. So the essential graph is going to have these 2 edges undirected and these 2 edges directed. And this is going to be a special type of partially directed acyclic graph, which is PDAG for short. And when we were talking about our example, we also said, okay, well, if the true graph had this x5 edge, then we can conclude that this graph also has the edge from x4 to x5, because if it was in the reverse direction, we would form a new unshielded collider. And generally, the orientations from the unshielded colliders are not going to be the only orientations that we're getting in the essential graph. And there's going to be a set of rules that you can kind of repeatedly apply if you just put in those orientations that you get from the unshielded colliders. If you apply these rules, then you'll get the essential graph. You might have to apply them over and over again, kind of until convergence. And these rules are called the Meek orientation rules, named after Christopher Meek, who introduced them. And it turns out we're going to need 4 of them. So the first one, let's just call this Meek rule 1, is that if we start with something with the form xk, it's going to xi, and then we don't know the direction of this edge, and then we also have that edge does not exist, then this becomes directed xi to xj. And generally, if I'm not putting an edge in, I just mean that edge doesn't exist. So we can think of this as kind of the, if we're thinking back to the term induced subgraph from either 1 or 2 lectures ago, then this would be an induced subgraph over xk, xi, and xj in the kind of the skeleton plus the orientation graph. I don't really have a name for that. Yep.
Sorry for asking about this again, but what was the intuition for finding unshielded colliders again?
Yes, so the intuition with being able to find unshielded colliders, say in this example, was that we can kind of tell that x1 and x4 behave differently when x2 and x3 are involved. So in particular, x1, any set that we have that is going to separate x2 and x3 has to include x1. And any set that that separates it has to not include x4, because if it included x4, it would create a collider there.
But, I mean, unshielded colliders, are they not found on the undirected graphs that you get from like the independences?
So unshielded collider by definition involves directions on the edges. Yeah, so we wouldn't say they're found in the undirected graphs, the skeleton. It's the skeleton plus you add in unshielded colliders.
See, I thought they
and
were
then
like,
you apply the Meek rules.
I see, I thought they were like the probable colliders in the undirected graph, but I guess they're really So what makes them unshielded then?
So unshielded is a property of the DAG, right? What we do is we first find the skeleton, and then we check conditional independences in order to add orientation. So it's not a property of an undirected graph. It's a property of either a partially directed graph or a DAG. Yeah. Okay, so Second Meek rule. We've already kind of implicitly used this multiple times when we said, okay, we're dealing with DAGs, so they're acyclic. So if we have something like xi to xk, then xk to xj, we have an undirected edge between xi and xj, we're going to be able to orient that into a directed edge. So these are kind of the two easy ones to remember. The other two can kind of be derived from those. So the third rule is going to say, if I have xi and xj, and these will both involve now two other nodes, so let's call them xu and xv, both pointing to xj. So this would be, these are not going to be adjacent, so this would be an unshielded collider. And then we say, don't have these edges. This is not forming an unshielded collider, right? So we know that the edges can be a non-collider, and there's three options for that. Well, the rationale here is that you always think of like, okay, I'm always giving you xi to xj is going to be the edge that's directed. So you always think in reverse, what happens if I direct xj to xi? We're going to show that that messes some things up. So what this is telling us is that now by rule 2, by acyclicity, we can't have the edge directed this way, so we'd have to have it directed this way, and similarly on this side, and we would form a new unshielded collider. So it's not possible that the edge is from xj to xi, it has to be from xi to xj. So in keeping with that, if we have a structure of this form, what we do is just replace that edge from to be from xi to xj. And finally, the fourth rule is also going to involve two extra nodes. So we're going to have xi, xj, we're going to have an xu and xv. And now the structure is going to be still that it's connected with undirected ones up here. But now instead of these both pointing to j, they form a chain like this. So let's think about what happens if xj goes to xi. Okay, then from this, from xv to xj to xi, we'd have to get the xv goes to xi. And then we would also get from an acyclicity this way, that it goes like that. And I believe this is forming another cycle or something. So I said, yeah, the contradiction here is that we have xj and xu not adjacent. So if I had xj directed to xi, then Meek Rule 1 would tell me that it should be oriented this way. So I get a contradiction of like that edge should be oriented both ways. So in particular, I'm going to have it this way. So these will come up in kind of our reasoning about what edges we learn from interventions. When you're just thinking about kind of the PC algorithm, what I think about is, kind of abstracting these away, write a little function that looks for like structures of this form in your current kind of partially directed acyclic graph, and then just repeatedly apply those until convergence. And we're going to denote that operation as mpdag of this, where this is a partially directed acyclic graph. And the M stands for maximal. So it's kind of maximally think it's actually written as maximally oriented, and then you just don't include the O. This is kind of the most edges that you can infer from the data that you have. So these are kind of just, this is applying kind of some rules of logic. Yep.
And just to be sure, the reason why Meek Rule 1 is a rule is because we don't want to generate like a new collider?
Correct.
I see.
Yeah. Yep. So it's basically, you think of, I'm starting off with, say, this graph, and then I'm asking for any of these edges, can I conclude anything about what the direction of that edge has to be? And I can always ask what would happen if I include it in one way versus the other. Some of them are okay to include in either way. They won't lead to any kind of things that, they won't lead to any new unshielded colliders or cycles or anything. But the ones that do lead to new unshielded colliders or cycles are these. And there's actually, yeah, I guess, so I kind of talked through the soundness of these rules, that these are correct inferences. And what we're not doing is actually showing that just repeating this operation gives you back the essential graph always. So that's stated as like a theorem in the lecture notes, but that's not something we're going to have time to prove. Okay. So before getting into our first structure learning algorithm, I want to kind of motivate some assumptions that we're going to have to make in order for that algorithm to be correct. And this was this whole idea that we discussed when we were going through the example of how we would learn this, of we have conditional independences in the data. Can we say that those actually imply something about deseparations in the data generating DAG? So we have one direction of implication, which is Markovianity, which is that the deseparations in the DAG imply conditional independences. We have to at least partially be able to go back the other way. And we can't always do this. There are pathological cases, kind of degenerate cases, where you would have extra kind of conditional independences in your distribution that aren't reflected by deseparations in the DAG. And kind of the simplest example one can give, other than like a trivial 2-node example where the edge just has like weight 0 or something, is with these 3 nodes. So say this is a linear DAG model. So we have x1 is epsilon 1, x2 is equal to a times x1 plus some epsilon 2, and x3 is equal to b times x1 plus c times x2 plus epsilon 3. Then plugging in the equation for x2, what we're going to get, for x2, we're going to get that this is equal to b plus a times c, x1 plus c epsilon 2 plus epsilon 3. And what happens is that if we look at the covariance, which let's recall in a Gaussian distribution, so let's say all of these variables are normal, then the covariance being equal to 0 is exactly the same as a conditional independence. So the covariance between x1 and x3 is just given by, I can plug epsilon 1 in here, and then again I can take just the product of those and compute the expectation. If we're in a DAG model, all of the epsilon 1, epsilon 2, epsilon 1, epsilon 3, all these pairwise things are have 0 correlation. So this covariance is just going to be, say, B plus AC times whatever the variance of that epsilon 1 term is. And if we have B plus AC equals 0, then we're going to have x1 is independent in the distribution from x3, even though they're not deseparated in the graph. And what we have to do to get rid of this is, you can kind of think of it, if you're thinking of these linear graphs, as like assuming that there are no kind of these cancellations, right? So we're like kind of have to tune these variables precisely. If you give me a value of b and a, I can solve for the value of c. If I just slightly perturb that value of c, then this equation would no longer hold. So we're trying to make some sort of genericity assumption. In kind of non-linear models, non-parametric models, we just state it directly in terms of the conditional independences. And that is going to be called the faithfulness assumption. So we say p of x is faithful to G if its set of conditional independences. So usually we just had that all of the conditional independences of the DAG are a subset. Now we're just going to say they're equal. So basically, every conditional independence in the probability distribution actually kind of comes from the graph structure. It's given rise to by the graph structure and not by kind of like a choice of coefficients or choice of functions like this. And the kind of justification for this faithfulness assumption is in like linear models, discrete models, other like parametric models. That's usually the case, is that you kind of imagine like randomly sampling these parameters. So put like some continuous distribution over the space of like all of the parameters. If you have, you know, say the graph of size p, and you have like O of p squared parameters, and you put some distribution on like R of p squared. Then if you make that distribution kind of continuous with respect to that underlying Lebesgue measure, then the probability that you sample some parameters that violate this is 0. In other words, the set of parameters violating this has Lebesgue measure 0. You can kind of arrive at that through some arguments about polynomials that are not identically equal to 0 vanishing. So this gets into some fun algebraic geometry type stuff, which we won't talk about in this course. The problem with that kind of justification, though, is that it only tells you what the size of that set where this constraint is like precisely violated. It only tells you about the actual 0 set of like these polynomials, and it doesn't tell you when those polynomials are, say, like epsilon close to 0. So they're really, really close to being 0. And when we have data, you know, we can't tell something that's really close to 0 apart from something that is 0. So usually people will talk about like a lambda strong faithfulness, where, say, if we're in the linear setting, what we want to do is bound like partial correlation coefficients. This would be like the partial correlation, say, I think in the P set, I'm using something like this. The partial correlation of xi and xj given a set S. We want those to be bounded away from 0. And kind of the statistical rates that we're going to get are going to depend on how far away they can be. We can bound them from 0. But then, you know, those sets go from being something of Lebesgue measure 0 to something of like higher volume, like actual positive volume. And then these might actually like be things that occur in practice. So typically we don't want to make kind of this full strong faithfulness assumption. We want to kind of look at our algorithm and see what conditional independences it's actually relying on in order to you know, correctly return the graph. And that's going to motivate us to kind of be more precise about saying which of the conditional independences in this distribution have to imply conditional independences in this distribution. So that's going to be the next two definitions, or the forms of faithfulness that we need for our first constraint-based algorithm. Any questions before I write those up? Okay. So one very desirable type of faithfulness, and you'll see that these both kind of reflect this characterization that we have. So we have to get the skeleton right, and we have to get the unshielded colliders right. Well, in order to get the skeleton right, what we're going to need is that our distribution, p of x, is what we call adjacency faithful to G if whenever xi is adjacent to xj in G, then there does not exist any set that can be used to render those independent. Right? Or in reverse, whenever there does exist a set that makes xi and xj independent, conditionally independent, that would have to imply that they're not adjacent. So this kind of gives us a one-to-one correspondence between nodes that can be separated by conditional independences and nodes that are adjacent or not adjacent. And the other thing that we have to get right is the unshielded colliders. So we say p of x is orientation faithful to our graph G if for all basically these won't be colliders yet, they'll just be triples of vertices that are kind of unshielded. So we want xi not adjacent to xj. So anytime we see a structure like this in this induced subgraph over just these three nodes, what do we have? If it's a collider, what do we want? Then for all sets that render xi and xj conditionally independent, we don't have the collider in that set. Right? Because if we were just looking at the graph and we include the collider in that set, then there should be a deconnecting path between them. And then if it's not, so any other kind of form of non-collider between these three nodes, then again for all s such that they're independent, then xk does have to be an s. Because otherwise, if we had something like xi to xk to xj, and xk was not an s, then we would have a deconnecting path here. Okay. And I won't write this on the board, but it's in the notes. Remember, because this will be in the theorem statement for the PC algorithm, is that if P of x is both orientation faithful and adjacency faithful, then we call that restricted faithfulness. So we just have one term kind of to capture both of those terms. Okay. So first I'll write out how the PC algorithm works, and then I'll show that under these assumptions that's correct, and I'll give a short runtime analysis of how long it will take to run. So kind of a note on how I'm going to present the PC algorithm. This is really the way I think about it, is that you kind of specify abstractly your input is not necessarily, say, like a probability distribution, like P of x. You specify a conditional independence tester. So this could be the probability distribution P of x. It could also be, say you have real data, then it's a function that you can ask, is xi conditionally independent of xj given my set S, and it will perform maybe some hypothesis test and say yes or no. So it just is kind of this submodule or something that answers the function, answers the question, is xi independent of xj given S? And then when we want to talk about kind of the consistency guarantees of the PC algorithm, then we think about, okay, the way that this conditional independence tester is answering those queries is by actually looking at the distribution P of x. If we're thinking about the sample version and trying to analyze that, then we can talk about which conditional independence test it's using. In the homework, you'll get a chance to work with linear models and use partial correlations for conditional independence testing. You'll be walked through step by step how to do that. Okay, so the PC algorithm, we have as input this conditional independence tester, which we'll denote by H. And then we're going to want to output two things. I guess I'm starting off, this is the first phase of the PC algorithm, which is just going to give us the skeleton. So it's going to give us a skeleton, G hat, along with something that we'll need to use in our next phase, which is going to be the phase that adds kind of this orientation. And we'll just be kind of saving these to, like, if you're implementing it in Python, you might do this as a dictionary or something. So, the first step is I'm just going to initialize with the complete graph. This is all undirected. So I'm assuming something that's input to this algorithm comes with the information of how many nodes there are that you're learning from. And then it's going to have this kind of current bound on what sizes of conditioning sets that we want to consider. So kind of historically, the first algorithm that was proposed to do this just kind of considered all conditioning sets and just looked for like any conditioning set that renders, say, xi and xj conditionally independent. If you're thinking about that for every pair of nodes, there's p minus 2 other nodes, so it's like 2 to the p minus 2 total sets. You don't want to enumerate over all of those. And it turns out, you'll see in our analysis of the PC algorithm, that it's kind of adaptive to the degree of the underlying graph. So if you have a really sparse graph, it won't take as long to run. And that's basically because this D, you're not going to let get so high. So what you're doing is you're saying while there exists some pair xi and xj, so I'm just saying these are adjacent in G hat, such that one of their sets of adjacencies in this graph is greater than 0, or sorry, greater than or equal to d. So if we've already surpassed all of these sets being less than d, we're kind of done, and we'll just exit this while loop. And we're going to say, okay, if there exists one of these, then we check for each pair of nodes, of adjacent nodes in G hat. What do we do? You could write this as a for loop, or you could just kind of like, the way I'll write it, to just say if there exists some set S that's a subset of the adjacencies of one of those nodes in this edge, that's of size d. So we've already checked all of the sets of size less than d. Now we're just like going one step further, checking sets of size d. So if there exists such a set such that xi is, our conditional independence tester tells us xi is independent of xj, given that S, we'll remove that edge, because that's basically our certificate that those are not adjacent, and that's coming from that adjacency faithfulness assumption. And then we're going to kind of save what set we used to separate them. So we're just going to set this, this separator function. We're just going to put xi, xj is now going to be this set S. And that's going to go as input into the second phase of the algorithm. And then I guess D has to increment at some point. So just after you've checked all of the edges in the graph, then we can write D equals D plus 1. Okay. So this should be your first taste of this algorithm. Give you some of the ideas behind it. I think implementing it is going to be the thing that really helps you see how it's working. Cool. Right. So the orientation phase, we're going to be taking as input the things that we've learned from the skeleton phase. So both the skeleton and then that separator function, and then this is much simpler. Okay, so this orientation phase. It's going to take as input that G hat S. And then what it's going to do is look now for all of these kind of unshielded triples. It'll just check if that xk was or was not separating. It was not, was or was not in that separating set. So if it was not in that separating set, then from the orientation faithfulness condition, we can conclude that xi xj form a collider at xk. Okay, and then the PC algorithm together is just literally running these two phases, with the input of this one being the output of that one. Okay. I guess we have some intuition that this is consistent. So I'll just give the statement and maybe jot down a few things about that proof. So we're going to say the PC algorithm with like H being our true distribution. So this is kind of the infinite data limit. The PC algorithm with that conditional independence testing returns G hat equals to, I guess, something in the Markov equivalence class of G, or we could say it returns the essential graph of G. So the last part of the PC orient algorithm is just going to be that it's returning it'll return basically the MP tag. So we'll apply the Meek rules at the end of this algorithm. Those are a little bit of a pain to orient, so in the pset you won't have to write out this step. You'll just do it by hand for your specific example, but you'll write the general purpose function for the rest of the PCL. Okay. So first we want to show that the PC skeleton step returns the skeleton. This is basically an inductive argument. Say that it hasn't removed any edges incorrectly so far. At the beginning this is true, that's our base case. Then we want to argue that it won't incorrectly remove an edge. Whenever we remove an edge, we actually should be removing it, right? And that's following simply from the fact that we've assumed adjacency faithfulness. So if we remove an edge, the only time that happens is if there's a set that's separating them. And by adjacency faithfulness, that implies that that edge is not in the graph. And then we do correctly remove an edge if we're supposed to remove it, right? Because there will be some set S that separates these, the parent set, say, of one of those variables, if they're not adjacent. And if we're never incorrectly removing edges, the parents are always a subset of the nodes that are adjacent to our graph, or node xi in the skeleton, right? So we'll always eventually be able to find that parent set and separate them. Okay. And then for the orientation phase, it's almost literally just like by definition of orientation faithfulness. So if xk is the thing that's separating them, then is not in the set that's separating them, then it must be, this is just kind of the reverse of this, that there is a edge. Or I guess it's the reverse of this bottom one, right? It can't be a non-collider if S is not in that set. And vice versa. So we're going to get both unshielded colliders and the kind of unshielded non-colliders, right, in the second step. Okay. And then why did we do it this way, where we have to kind of keep track of this D variable? As suggested, this is kind of both for the runtime analysis, which is what we'll do here, and then also the statistical analysis. I guess a point about all of this stuff in practice, conditional independence testing, is that as the conditional independence set sizes get larger, then both kind of your statistics for testing whether or not two things are conditionally independent, those are going to become more expensive to compute. And they're also going to have statistically less power, because usually what you have to do is something like in a non-parametric setting, you'd have to regress xi on S and xj on S. So if you have like a large dimensional S, you need more and more samples in order to do that in a statistically sound way. So yeah, always think about like when we're using kind of conditional independence testing somewhere in here, not just how many tests are performed, also what sizes of them, what sizes of conditioning sets we're using to perform. So I could add as maybe an additional proposition or something that we only use conditioning sets up to size, like the number of adjacencies for some variable. Yeah.
Sorry, I might have missed that, but are the Meek rules implied by PC orient?
The Meek rules, this last step
Yep.
is what's running the Meek rules. So I didn't define this, but yeah.
Sounds good.
Yeah. And PDAG you can call the closure of the partially directed acyclic graph under the Meek rules. Great. So let G be a DAG with maximum degree delta, and this is not in degree, this is like kind of full degree, both like the number of parents and children. So delta, if you want, is the maximum over nodes of the number of adjacent variables in this graph. And then again, I'm kind of thinking about running the PC algorithm in this kind of Oracle population setting where I'm using the true distribution. So PC skeleton terminates with D less than or equal to delta plus 1. So first is when D equals the maximum in degree. So this is just if we replace the adjacency set there by the parent set. At the end of that round, G hat is equal already to the skeleton of G. And that's because by then we've been able to consider all parent sets. So if any two nodes are not adjacent, then we've looked at their parent set and said, okay, they're not adjacent. We can remove this edge. So after that, G hat is now the skeleton of G, so the number of adjacencies in G hat is, for all of the nodes, is just equal to the number of adjacencies in exactly the true graph for that node. We didn't need the cardinality, it's the same adjacencies, literally by definition of the skeleton. So if once we get to the last node, once we get to the node that has delta neighbors, and then we increment to delta plus 1, then that while loop is going to break. So the consequence of this is just going to be that under those same conditions, the query complexity, which I'll define in a second, is p to the delta plus 2. So query complexity is how many times it asks that conditional independence tester is xi independent of xj given s. If you want like a full runtime analysis, then you have to actually go in and specify how you're performing the conditional independence tests. So this kind of gives you a more general result where then you can just go in and multiply by the number, or at least that will give you an upper bound, is multiplying by like the maximum complexity of any of those conditional independence tests. And those can get pretty expensive, so if you're thinking about non-conditional or non-parametric conditional independence tests, those are usually based on kind of these like kernel statistics that require computing a kernel matrix, which is like number of samples by number of samples, and inverting it. So in particular, you'll get some like cubic dependence on the number of samples. You can get that down to like quadratic dependence. I think I've seen, if n is the number of samples, I think I've seen n log n. But you know, there's always these like kind of computational statistical trade-offs. So this is all to say, you know, this is kind of staying at a level of abstraction, so that you can kind of plug and play with different results. I didn't want to give you just the one for, say, partial correlation testing. So just the proof of this almost just follows from that lemma. So we consider in each round p squared nodes, or pairs of nodes, I guess. And then if we just consider for each node, or for each pair of nodes, kind of what is the maximum number of conditioning sets that we're going to consider. It's basically the sum over d prime, ranging from, it starts at 0, and then we said it will end by delta, and then the number of subsets of, I guess this should be, put p in the nodes, but like p minus 2 at most, choose d prime. The number of subsets of a set of p choose 2 elements that are of size d prime is p minus 2 choose d prime. And then this adds up to something that's O of p to the delta. So it's kind of dominated by the maximum size that we're considering. And this is all big O notation, so this is saying this is an upper bound on the complexity of the algorithm. You might be able to get like a more refined analysis by considering particular aspects of the graph. But I think at least if you choose like delta, say much smaller than p, which is normally maybe what we're considering, is like these sparse graphs, then this should be more or less a type analysis. Okay. So I'm going to erase the boards, give us like a 5-minute break, and then I'm going to talk about some other causal structure learning algorithms. If y'all want to go to the bathroom or do anything, ask any questions. Okay. So for the rest of the class, we're going to focus on kind of the principles behind some of the score-based structure learning algorithms. So instead of, first testing conditional independence and then trying to figure out what those conditional independences imply about the graph under the faithfulness assumption, the kind of principle behind these is to develop a search space, either over graphs, or one of the ones that we'll see is over permutations of the nodes. And for each of those, assign a score to them, and then try to either maximize or minimize the score. You can always make it say maximization. So higher score, better fit. And one of the ways that you can start thinking about structured learning, even before we start talking about identifiability of the true model, is just say I don't want to find the true model, but I want to find kind of any model that fits the data. So in particular, kind of the sad thing is that the complete graph will always fit the data because it implies no conditional independences, so you can always fit anything to it. So on top of kind of saying that we want to fit it, we can also say that we want to fit it in kind of the minimal way. And that's going to lead us to our definition of a minimal IMAP. So first, an IMAP or an independence map will pretty much always see IMAP. The I does stand for independence, but an IMAP G of distribution P of X is a DAG. It could be another type of graphical model, but we're focusing on DAGs. So it's a DAG such that, and you've seen this before, it's just saying that P of X is Markov to G. So this is kind of just like the reverse terminology, teacher and student. Like the P of X is Markov to G. G is an IMAP P of X. Same thing. So a minimal IMAP is an IMAP such that no subgraph is an IMAP. So you can get multiple IMAPs, minimal IMAPs for distribution. The true graph, under faithfulness type assumptions will be one of them. I guess you can also extend this terminology to two DAGs. So let's also say H is an IMAP of G if that inclusion holds. So let's just kind of think about this at the graphical level for now, instead of always saying P of X is faithful or whatever to G, and thinking about the IMAPs or minimal IMAPs of that. So let's just say that we have G being our graph we've been using. Then the claim is that this graph is also an IMAP of G. So I'll always have the same adjacencies for an IMAP. But then, this is a minimal IMAP of G. So I'll always have the same adjacencies. It's clear that I can't get rid of those, otherwise I'd introduce some set which those two nodes would be conditionally independent, whereas they're not. That conditional independence is not implied by this graph. Now what happens, we have this extra edge, so this is really the only one that we have to check whether or not we can remove it when we're testing for our definition of minimality. Well, if we remove that edge, can anybody see what conditional independence that will imply? That is not true. That would imply x2 is, if we remove this, that implies x2 is deseparated from x3 unconditionally, because we only have these two paths that go through colliders. So if we're not conditioning on anything, then these would be deseparated. Whereas in this graph, they're not deseparated, given that desep. And we have a way to construct basically all of the minimal IMAPs of a graph. And that's where permutations come in. I guess one way to construct all minimal IMAPs would be to just enumerate over all graphs on P nodes and check. Or even say that you just want to find one minimal IMAP of a distribution, P of x. You could either apply the PC algorithm and learn the data generating one, or do something like enumerate. But you don't even have to apply the PC algorithm. You can always just give me a fixed ordering of the vertices, and I can spit back an IMAP for you. The procedure I'm going to define for that will require one assumption. I think it's weaker, or at least incomparable to faithfulness. Yeah, it's weaker. Faithfulness would imply this assumption. And it's also just a good opportunity to learn some terminology that people use when talking about graphical models, DAGs, undirected graphs, a bunch of other ones, like ones that include stuff for latent confounding. So that is what is called a semi-graphoid. And we've already seen these in 3 different ways. So these are collections. Of disjoint subsets. A, B, and S. So let's say this is a graphoid on a semi-graphoid on calligraphic X. So these are subsets of X. And we'll just denote inclusion of one of these tuples in the set by this independence operator. This says the tuple A, B, and S belong to the semi-graphoid H. That's just our shorthand. And we need the following properties to hold. So if A, B, S is an H, that implies B, AS is an H. So this is symmetry. This is the most trivial one. Then we're going to have what we call decomposition. which says that if we have A, B, S in H, then we can basically kind of marginalize. So we can also say that B prime S is in H for any subset. So it's closed under, taking subsets of either of the first two. I'll just continue this on the next board. Weak union. So if I have this, then I can move, here I was just taking a subset and kind of only, I was completely getting rid of the rest of B. This is just going to keep the rest of the B, but put it on the other side. So this is B just being the disjoint union of B1 and B2. And it will also satisfy this final property called contraction, which says that if I'm independent of this kind of a partial converse, I believe, to the weak union. So if I'm independent, I have this independence kind of in the semi-graphoid H, and I have the reverse one, so I can also do it this other way. Then I can put those together on the side. So this is how conditional probability works. These are all, I guess, for any probability distribution, the conditional independence relation is a semi-graphic. Maybe I'll assign that or something about semi-graphoids with either undirected or directed graphs as part of the one of the homeworks. So we said conditional independence always satisfies this. What we're going to need for the construction to hold is the thing that takes a semi-graphoid and makes it into a graphoid. So a graphoid is a semi-graphoid that also satisfies this intersection property. And this says hold on. That is what I think I wrote down as the contraction property. The contraction property shouldn't have this. The intersection property is the one that has the. So one of the takeaways from this is that nobody ever remembers all of these properties, no matter how much we've worked with them. And I have not worked with them in a while, but I suggest, writing this down cleanly somewhere and then having it to refer back to if you ever do end up using it. You'll forget it over a weekend, probably. So why is this intersection property not always true with a probability distribution? Let's even take it with S being the empty set. So what I want to give you is an example where we have A, B1, and B2, such that A is conditionally independent in this distribution from B2 given B1, and A is conditionally independent in this distribution from B1 given B2, but A is not conditionally independent from the pair B1, B2. So this is the same implication, right, as this. And here I'm always defining B as the disjoint union of these two. Okay, this is a really simple example actually. So I can have B1 and B2, A. Let's say they're generated from a causal graph like this, and then I have B1 is Bernoulli, probability half, B2 is Bernoulli with probability half, and A is just deterministically equal to the XOR of B1 and B2. Well then the probability A equals 0 or 1 is 0.5. The probability A equals 0 or 1 conditioned on either B1 or on B2 is still 0.5. Oh, sorry. Did I just completely write this out? I'm not sure. I mean, this still holds for this example. There's not exactly the conditional independence statements that I was thinking about. But it's definitely not conditionally independent of both of them, right? Because if I know both of them, then it's deterministically assigned. And there's a result that says if the distribution over these variables is strictly positive, so it's bounded away from 0 for all values that these variables can take on, then P is a graphoid. So it's sufficient to say that the distribution is positive. That will imply that it's a graphoid. Not necessary. So graphoid is kind of like the right level of abstraction for which a lot of properties hold. If you think back to when we were talking about the relationship between factorization and Markovianity in undirected graphs, we also said something about needing positivity of the distribution to go the opposite way and to say that Markovianity implied factorization. I think just the graphoid property is sufficient for that as well. There's a little connection there. Okay, going on. So the reason that we introduced this was to say that we can construct a minimal IMAP for a permutation. So proposition, we'll say P of X is a distribution, pi of permutation. And then we're going to define G pi to be a DAG with edges, and it will have xi going to xj. So we need that it respects the, like this will be a DAG with pi as its topological order. In the last lecture I was writing this as pi of xi comes before pi of xj. This is just more compact notation for the same thing. Don't write pi twice. So in that permutation, xi comes before xj, and xi will only have an edge when xi is not conditionally independent of xj given everything that comes before xj in a permutation other than xi. So the way I kind of think about this, let's go back to this example. The way I think about this is that I write out an order. So I have 2, 3, say 1, 4, 5 for this one. And then I kind of go pair by pair and check. And as I've said, we're always going to have the adjacency, so I just have the same adjacencies as the original graph. So I just have to check things that were not adjacent in the original graph. So our 2 and 3 conditionally independent given the empty set. That's what comes before. No, because they have that deconnected path. And that's why we get the edge here. Then if we look at any of the other pairs that were not connected, so 2 and 5, are they conditionally independent given 3, 1, and 4? Yes. And then similarly, if I do 3 and 5, they'll be separated. 1 and 5 will be separated, so I don't get any of those extra edges to 5. So this gives us kind of a way of generating. This would be G 1, 2, 3, 1, 4, 5. We can try a different one. So say that I gave you the permutation 2, 4, 1, 3, 5. So we're just going to go through and all the edges that I already know are there, we just put them in the right orientation. So 2 comes before 4, 2 comes before 1, 2 comes, yeah, the other 2 aren't adjacent in the original graph. 1 came before 3, 4 came before 3, and 4 came before 5. And then let's check all those missing edges. So do I add the edge from 2 to 3? Well, are 2 and 3 conditionally independent given 4 and 1? No, because I open up this path when I condition on 4. So I get this edge. And then are 4 and 1 conditionally independent given just 2? So now I'm no longer including 3 before I check 1 and 4. So no, and 4 comes before 1. So I have it this way. 5 is still at the end. So 4 is always kind of coming before it when I check anything. So I'm not going to get any extra edges to 5. So my minimal IMAPs can either have, you know, the same number of edges as my true graph or more edges. And the proof that this construction is going to give us a minimal IMAP basically comes from saying that first we're just gonna, well, we're basically gonna want to prove that p of x factorizes according to the graph, and you know, we can do something kind of similar as to when we were proving the Markovianity implied factorization, which was, I think, the easy direction to remember. So that we kind of wrote it out according to the total probabilities, or the chain rule probability, according to this order. And then we got these terms where we had xi given everything that came, or xj given, say, everything that came before it. And what we want to show is that we're going to replace that conditioning set with just the parents. So if we take 2 nodes, say, that are coming before xj, but are not its parents in this graph. We'll use this intersection property with S being equal to this set where we subtract both xu and xv out. I guess this is parents g pi, right? So we have that first xu is conditionally independent of xj given that set S along with xv. And then we have the reverse thing for xv, xj, and then S along with this with xu. So the intersection property is just letting us combine the xu and the xv into this set here. So we kind of reduce the size from everything before it to except for one variable, except for either just xu or xv, to everything before it except for two variables. And then we can just iterate on that and get that it will be, so we can do that always with any parent set. We can continue this argument. Okay. Another thing to say about this, when we're talking about the PC algorithm, we were talking about really big conditioning sets being bad. So here, you're eventually with the last variable going to be conditioning on p minus 2 other variables. So this is kind of, in practice, not the ideal way to be constructing a minimal IMAP. You can do kind of more clever things. The reason the definition that we have here, in my opinion, doesn't, like what you're kind of trading off for, like if you're thinking about implementing this computationally or statistically, is that this just defines it kind of in one line. It says for each edge, just a single conditional independence that you have to test. So, you know, I could send my data to like p choose 2 separate like servers and just run all of these conditional independence tests in parallel. The other ways that you would want to do it for like more computational or statistical reasons would be more serial. So you would like start from the top of the topological order and then decide which things to add, or maybe the bottom, I think works as well. Okay. So you should probably have the intuition that if we take the right topological order and put it through this procedure, like any topological order of the true graph, it will return back the true graph. That is true under the faithfulness assumption. If we don't fully make the faithfulness assumption, then we are guaranteed to return at least a subgraph. I'm not going to prove that. That's in the notes. What I want to prove is that if we kind of search over all permutations, then construct this g of pi for all of those permutations, the ones which return the sparsest g of pi are always Markov equivalent to the true graph. So that will kind of motivate using sparsity of minimal IMAPs as a way of scoring our graphs. And that's kind of the main principle behind two of the score-based searches that I'll mention. So if we let pi hat be a minimizer of the number of edges in this g pi, so whenever I take a graph and put cardinality, I'm just going to be number of edges in that graph. So and this is coming from, I could also put maybe in parentheses some distribution p of x. So part A is the thing that I just decided to skip, which is that basically you can always get smaller than the true graph. So this is if this is Markov to our graph G. Under that condition, you can always find something at least as small as the true graph. We additionally add adjacency faithfulness. Then we'll get the skeleton of this G pi hat is equal to the skeleton of our true graph. And then if we add in restricted faithfulness, so both adjacency faithfulness and orientation faithfulness, then we'll get that this G pi hat is in the Markov equivalence class of our true graph. So part B, basically follows from part A and adjacency faithfulness. So I know that I can get at least as small as the true graph, and then additionally by adjacency faithfulness, anytime that I test two nodes that actually are adjacent in the true graph, there can't be any set that separates them. So really, well, I'm gonna write out the C. So if we have an unshielded collider in the true graph G, now let's consider some ordering where we put this xk before one of those variables. And then, I mean, it kind of becomes this case-based thing, right? Like if xk is before this, it could still be that like xi comes before xj, and then the thing that we're looking at is when we're conditioning, we're looking at the test, this given everything that comes before it, and in particular, this set that comes before it is going to include xk, and then by orientation faithfulness, these are not going to be conditionally independent given that set that we're testing. So we're going to get an edge from xi to xj. So we're going to have more edges than the original graph. So any order that we consider where like a collider is in the wrong order, the case xk coming before xj is independent. There is symmetric. So we're always going to end up getting this extra edge. And that was kind of what was happening with our examples there. It's like when we put, say, the collider 4 between 2 and 3, we got an extra edge between 2 and 3. And then, so we've shown basically that if G pi hat is as sparse as G, then any unshielded collider in G also has to be an unshielded collider in G pi hat, and then we want to show that G pi hat doesn't have any extra unshielded colliders, and then that will give us Markov equivalence. So if instead we had a non-collider, we basically consider the case where we put xk after both of them. So that in our graph G pi hat, we would be having a collider, and then we show that would end up creating an extra edge between them, and that's because when we're testing xi to xj, that set S for whichever one is coming later will not include xk. This is again by orientation faithfulness. Then if a set doesn't include xk, and this is non-collider, then it should be deconnected. Okay, so that gives us what would be called the sparsest permutation algorithm, which is enumerate over all permutations. For each permutation, look at the minimal IMAP, and then return the sparsest one. Of course, that's still like enumeration. That's not great. It's over the space of permutations instead of the space of graphs. Slightly smaller, but still not great. So the greedy sparsest permutation algorithm actually does a search over that space of permutations in order to find the sparsest one. The idea is that you initialize at one permutation. There's kind of some heuristics that you can use to start with a sparser one. And then you're going to kind of move around in your space of permutations to try to find a smaller one. And the last thing that we're not really going to prove, because it's a super long proof, it would take probably a whole lecture to do, is basically that that procedure is consistent. So the way that we want to search around, we want to, if we're thinking of starting at some minimal IMAP that has more edges, what we want to be able to do is delete edges. And then sometimes, if it's a minimal IMAP, we can't delete edges from that graph. We have to find maybe another Markov equivalent graph that we can delete edges from. So how do we explore within that Markov equivalence class? And the solution is going to be in terms of a special type of edge in a graph called a covered edge. So we call xi to xj a covered edge. If basically they have the same parents, but xi can't be a parent of itself, right? So we'll just say that the only parents of xj that are not parents of xi is xi itself. And I guess additionally, we shouldn't have any parents of xi that are not also parents of xj. So it should be that this actually equals the union of those two sets. So these, yeah, they're just, the parent sets are equivalent except for this one particular thing. And then if we reverse this, right, it is still a covered edge, just in the reverse direction. And we have a proof in the notes that if you take a graph, G, and you reverse a covered edge, then G prime is Markov equivalent to G. There's several ways you can prove this, either by factorization or looking at unshielded colliders. It's clear that their skeletons remain the same. So the key thing that makes all of these algorithms work is a statement that basically covered edge reversals and edge deletions are enough to get you between any graph and an IMAP of that graph. And in particular, like for these algorithms, what we're thinking about is the true graph is kind of the one that we want to get down to. And it's typically stated kind of in the reverse direction. So if we say that if H, so that's a DAG, is an IMAP of G, then a Chickering sequence. This is named after Max Chickering, who's the one who proved this. It was a pretty major result in kind of this greedy structure learning at the time, 2002. So the Chickering sequence is a sequence of graphs G1 to GM. So let's just say that this is equal to H, and this is equal to G. So it's a sequence of these graphs such that GM is obtained from GM minus 1 with an edge addition or a covered edge reversal. So there's a picture of such a sequence in the notes that I want to draw out and make some remarks, and we can wrap up. Just to give you kind of a visualization of how I'd like you to think about one of these sequences. So maybe we want to remember what a covered edge is. We'll do it here, and we'll try to go from this graph G to this minimal IMAP of it. So let's just say we have that graph. I won't put the x's, just to save some space. Let's say we have this graph, and we want to get over to the graph here. Now the proof of this, it's actually really nice and constructive. So what it does is, and this is the reason that it's phrased in terms of edge additions instead of edge deletions, it starts at this graph G, and then it tells you one operation on it, either an edge addition or a covered edge reversal, that you'll have some distance between G, your current iterate, GM, and this final graph that you want to get to. And that distance will be basically measured in terms of like the number of edges that are wrong and the number of edges that are missing. And what it will do is give you a graph that is less. So this is going to form a decreasing sequence. And if you start at a finite distance away and then you're always monotonically decreasing, you'll eventually get there. So That's called the apply edge operation. I actually didn't check that this example is exactly what the apply edge operation would do. It is a Chickering sequence. I guess the one that you get from the kind of proof in there of like repeatedly using this apply edge operation, you might call like a canonical Chickering sequence or something. And they have several kind of nice properties. But for this, I can just add. I don't want to write out all of the edges again. So copy this whole graph and then add the edge 2 to 3. Now we're going to kind of explore within a Markov equivalence class. So we've just kind of bumped up to a different Markov equivalence class. How do we explore within that? So we can use these covered edge reversals. Note that a corollary of our result that we can always get from G to H, which is an IMAP of it, by additions and reversals, is that we can explore a whole Markov equivalence class just by reversals, right? Because we can have one of these sequences, but that sequence can't include any edge additions, or else we would get out of that equivalence class because we'd be changing the skeleton. So that's kind of the way to think about this, as we're using covered edge reversals to explore the class. And in particular, the covered edges in this graph are the edge from 1 to 2, and it turns out the edge from 1 to 3. So I'll just add in that so that you can see it. I won't be lazy, I'll just add all these. So we can flip either of those to explore. Let's flip the x2 to x1 edge, so we get this. Okay, that's going to give us a new set of edges. We just flipped this edge, so that should still be a covered edge. We've made this edge not covered anymore because 3 has 1 as a parent. That's not a parent of 2, but this edge is now covered because both of them have just 2 as their only other parent. And then we can flip that one. So we get the graph with 3 to 1. And now we're going to add an edge. So we'll add the edge. Now we've made it so that 1 is not downstream of, or 1 is not an ancestor of 4 anymore. So we can actually add an edge from 1 to 4, or so, sorry, from 4 to 1. So you can kind of see we're getting closer and closer to this graph. And then I think it takes one additional operation. And that's going to be, or I guess 2, because there's one more graph in the middle, is what I'm trying to say. So if we write all of these out, it'll be more easy for us. So it was this edge that we wanted to flip and check for it being, oh, and I missed that, right? Okay. And then these should just be one edge reversal away from each other, this one covered edge reversal. Okay, so the idea of the greedy-Sparsest permutation algorithm, this kind of construction of a Chickering sequence says I know both G and H, but in practice you are trying to find this G. This would be the graph that you're trying to learn. You initialize at some H, you kind of do this depth-first search over your Markov equivalence class in terms of covered edge reversals. One nice thing about that is when you just do a covered edge reversals, not a lot of the kind of topological ordering changes. So you only have to do a few conditional independence tests in order to kind of recompute what your minimal IMAP is. You can kind of, memoize most of your testing. And by this guarantee, eventually there is some graph in your Markov equivalence class that is not a minimal IMAP. So you can delete one of the edges. So that's just a corollary of the this Chickering sequence result. And then you just keep repeating that until you get to a graph and you start to kind of say either its whole Markov equivalence class, or in practice you would put some like bound on the search depth. You say, okay, I can't improve anymore. So that's the greedy sparsest permutation algorithm. And then the greedy equivalence search algorithm, kind of instead of considering just DAGs, it considers these essential graphs. So it considers kind of taking the whole Markov equivalence class as one object, and then figuring out whether you can do deletions. And it also has like kind of this forward phase where you start at the empty graph, and then you keep adding edges to build up to a minimal IMAP. So I'll wrap it there. I might start next time with some of the additional remarks on causal structure learning, just for everybody's curiosity. Thanks.